We have been comparing groups on a quantitative response variable, and in the previous videos, more recent videos, I've been talking about multiple comparison procedures. Now it's actually time to go ahead and implement these. So let me go ahead and run what we have done so far. Let me go ahead and do a run all on this so we can take a look back at our box plots to remind ourselves what these groups look like. We have here a table of descriptive statistics, and we're focusing primarily on means. So these are the sample means, 38.96, 36.92, and 24.92. What we want to know is, from these observations, from not only these means, but from the spread of the scores, that is the standard deviations, which we're going to translate into standard errors of contrast, what can we say about the differences in means outside of this study? That is, what can we infer? So description, I consider most important. It tells you what you actually learned from your study. But we're going to take the final step now, which is there anything we can say outside this study from these data? So I did some things down here at the bottom of this notebook in terms of showing you how to calculate contrast and variances of contrast. But now I'm going to turn my attention to the way we actually implement each of the three multiple comparison procedures that we learned about. Some of them actually two of the procedures we're going to pretty much be able to do without doing anything beneath the hood. The third one we're going to do a little bit beneath the hood simply because I'm using base R. There are packages available if you want to look into them so that they will do it for you. But we're going to use base R to use all three of the procedures, and it's not going to be too difficult, and I think it will help our learning along the way. So let's start with Tukey. That's what I consider about the most common, because I think the most common question we have is there any difference between individualist and hierarchicalist? Is there any difference between individualist and egalitarian, or is there any difference between hierarchicalist and egalitarian? And by difference, I'm talking about the differences in centers of the distribution. That is, the differences in those means of the distributions. So let's implement Tukey. In order to implement Tukey, I need to actually show you one other way to do an omnibus test. So let me go ahead and create a code chunk here. I'll remind you that the way that we did the omnibus test in the past, let's see if I can find it here. Here it is. We used the ANOVA for whatever our model was. So let me go ahead and do that again so we can remind ourselves what we get out. This will give us an ANOVA table, which is a very common thing to look at when you're comparing groups and you want to do inferences. So this ANOVA table is analysis of variance. It partitions out into the sums of squares due to our model and the sums of squares due to our residual, that is what's not explained by the model, and from those we can get mean squares, and from those mean squares we get an F that we can associate to a particular F distribution in order to get a p-value to see if we reject a null hypothesis or not when we're doing a hypothesis test about the equality of means. That is the omnibus test. This is for the omnibus testing. There's actually in base R an alternative method that we can use, and it is called AOV. And the AOV, analysis of variance, actually takes the place of both ANOVA and the linear model. Let me show you what I mean. So I'm going to create what I'm going to call an AOV model. Okay, that's going to be my object. Let me do it like this. I prefer underscores there. So that AOV model is, we use AOV, and then we set it up just like we did linear models. So we have plain risk for score is a function of plain risk for our categorical variable view. You notice that's identical to how we did it before with our model, except there we used a linear model. Here we're using AOV. So let me go ahead and run that, and it saves an AOV model. You can see in my environment now I have an AOV model, which has a whole bunch of the same kind of stuff that a linear model does. But this is required in order to run Tukey's procedure. And so let me show you what the output is of AOV model. That output is a different kind of analysis of variance table, not as informative as the one we got with ANOVA. It gives us the sums of squares for the model and the sum of squares for residual. It gives us the degrees of freedom, gives us this residual. Here's the residual standard error. If you're wondering what is the residual standard error, well, you just take the mean square error. So to get the mean square error, I'm going to do this up here in my console. I'm going to take 14,7,9,10.13 divided by 222. You take the sums of squares divided by degrees of freedom. And I think I missed something here. Let's see, 147, too many nines. 147,910.13 divided by 222. There we go. And now if I take the square root of that, so remember the square root of a variance is a standard deviation. And this is a standard deviation that's actually based upon means, so it's a standard error. That's the residual standard error, 25.81. Well, what is that? That is the common sampling distribution standard error for each of our means. So if you think about the fact that when we talk about needing homogeneity of variance, that's because we're using this as the common standard error, common meaning for all of our distributions. In our case, we have 3 of them. And so if you don't have homogeneity of variance, you shouldn't be using one number for that. But that's what this particular thing is here. That's the residual standard error. So you think about doing your sampling distribution of means and you have a standard error. There it is. Okay, so we saw that AOV model gives us something that's not quite as informative as a ANOVA model, but we can also get, let me go ahead and put in the same code chunk, we can also get a summary of the AOV model, and that looks like our regular ANOVA table right here. So this part is the summary part. Everything up above we already did a moment ago, down through the residual standard error. So this will now give us the ANOVA table that we know and love and that we're used to. So you can get that same ANOVA table out even if you do AOV model. Now again, why am I bothering to do AOV model when we already know how to make that ANOVA table? It's so that I can do Tukey. Tukey requires that you have saved your model in an AOV model. So let me show you now how we do Tukey. It's pretty straightforward. Once you have the AOV model, I'm going to put in a code chunk, and I'm going to put in Tukey HSD, which stands for honestly significant difference, and I'm going to put in my AOV model that I created right up here on line 160, and I run that, and there are my Tukey confidence intervals. Furthermore, if you want to get a picture of those confidence intervals, this has got some good and some bad to it. I never liked the way it titles this, but let's say, let me put Tukey results is going to be the Tukey HSD AOV model. So in other words, I'm saving my results instead of printing them out. If you do that, you can then put an additional line in which you say plot the Tukey results. And other than the title, this is kind of cool. You see how I don't like the title? The title is 95% family-wise confidence level. Why not have a title like Tukey confidence intervals? But here's a picture of the intervals, and you see one of them here, is actually fairly close to 0 in the center and goes a long ways on either side, whereas the other two intervals are all negative. Why negative? It's the way things are subtracted. So if you look up here at these, actually, you don't need to pay attention to this p adjusted. I don't want to, there's a reason for that and it has a meaning, but you really don't need that if you have confidence intervals. So let's look at these confidence intervals here. So this says if I take hierarchicalist minus individualist, and let's go back way to the top and remind ourselves, there wasn't much difference there. See the means, 38.96, 36.92. So this says if you take hierarchicalist minus individualist, that you're, in the way we subtract it, we got a -2. If you flip that around the other way, it would be a +2. And the same with these boundaries here. So this goes from -12.6 to +8.5. If I flip it to do individualist minus hierarchicalist, which you could do by hand, all you got to do is change all the signs. This becomes a +2, this becomes a +12, this becomes a -8.54. So that one is the one that corresponds to this interval that doesn't show like it's very informative, other than to tell you that there's not much difference between hierarchicalist and individualist. I guess it could get, if I look down here, it can get as much as about a 12-point difference. This one says, let me flip it around. Individualist minus egalitarian, there's a 14-point difference, and it would range from anywhere from +3 to +25. Again, I've mentally flipped this around to be the big number minus the small number, which is the way I tend to like to do it. Individualist minus egalitarian, I just rather think in positives than in a bunch of negatives. And so that is a 14-point difference ranging from 3 points to 25 points. Now that's a pretty wide interval, but it does tell you that the individualist has a higher perception of risk than egalitarian does. It might be as low as, in the population, remember we're talking about inferences now, it might be as low outside of this study as 3 points, but it could be as high as 25 points. Similarly, hierarchicalist minus egalitarian, 12-point difference, it could be as low as 3 points, could be as high as 21 points. So that's how you get Tukey intervals. Now again, a reminder, there's two different ways to do this. One is to skip the omnibus test. Now you might say, wait a minute, we didn't skip it. We had to run the AOV model. Yes, you did, but we didn't have to look at it. We could have done this. We could have taken and run this and then run this. If you use the model results in order to do an omnibus test, then how do you treat that differently? Well, if you do not reject the null hypothesis, you're done. You don't go on to Tukey. Because if you do go on to Tukey, you could end up inflating your type 1 error. It's for reasons that are rather subtle. The ANOVA model we're running is based upon an F-test. The Tukey model is based upon an omnibus range test. I'm not going to get into those details here, but you're basically switching from one method to another that don't always give the same results. And so if you want to maintain your type 1 error rate and you want to do an omnibus test, you can still do Tukey as long as you've done what we did here, and that was we were able to reject the null hypothesis. We see it down here with the AOV model as well, same thing. We're able to reject the null hypothesis, say there are mean differences, and now we go ahead and do Tukey. Alternatively, we could have skipped the omnibus test and gone right to Tukey. Would I have gotten the same intervals? Yes, I would have gotten the same intervals. But it's just to make sure you maintain your type 1 error. Now, if you're not worried about strict maintenance of your type 1 error, and I don't blame you if you're not worried about that, because actually we never exactly meet the conditions that we're expecting for or that we say that we need in order to be able to make valid inferences. So our inferences are not always really precise. Our p-values are always going to be a bit wrong. And so if you say, look, I just want to run Tukey intervals regardless of whether I did the omnibus test or not, I don't think anyone's going to yell at you for doing that. Okay. So that's Tukey. I think I'll go ahead and stop there and wait for Bonferroni for the next video. Tukey, most powerful, meaning the shortest confidence intervals for all pairs when you have met the conditions. Remember, one of the conditions is that you have homogeneity of variance. So there may be a time you do all pairs using Bonferroni and you say, hey, these are narrower. I'm only telling you this well, that might be because you didn't have homogeneity of variance. But if you've met all the conditions, the Tukey confidence intervals will be the narrowest. All right, in the next video, we'll talk about Bonferroni. I'll see you there.